Okay, so I got about 10 graphs we're going to analyze. And I'm going to, I think, just graph very quickly, but then I'll try to explain what I see. And one of my mentors, when I first started teaching math, I didn't know a heck of a lot. I feel sorry for the students who had me now. But he said, stages of learning are as follows in math. I'll do a problem for you. You try to follow it. Then you practice a little bit, do it for yourself. And then you explain it to someone because it really sinks it in. Well, I added up how many of these quadratics I graphed, and this was several years ago, and it was over 100,000, easily over 100,000, and it's a whole lot more than that now. So I should be able to explain it. I mean, you do something a couple 100,000 times, you're going to know something that somebody else may not realize because they haven't worked with it as much. And so I'm trying to save you all the time it took me to really get into what I'm seeing. So I'm just going to graph this real quick. I'll put the information that I'm hoping to see from a test from my students today. So I see 5x squared. First thing I do is I go for shape. I know I'm on the decreasing side, so I know 0, 7. And I also know that 20 divided by 5 is 4, cut in half is 2. And if I put a 2 in there, I get minus 40 minus 20 plus 7 is minus 13. So as far as I'm concerned, that's graph. And to get the symmetry, it's nice to do 4 comma 7 as well. All right, so that's basically it. Now, what are some of the things that I saw over time in graphing that particular function? So let me get rid of that. Well, the first thing was realizing that minus b over 2a gets me the x value. And we can see that from the standpoint of ax squared plus bx plus c equals 0, that's a rectangle. All right, and that rectangle is x times ax plus b. And if I add c, right, how am I going to get this thing to be equal to 0? Well, that's where the quadratic formula comes from. But on this topic, I can see that we'll pretend a is positive. So I've got a cup shape up. And I can see that what makes that 0 is either 0 or if I take the x out, if I take the a term out, it's x times a times x minus plus b over a. Here, I finally got that. So that's minus b over a. I'm sorry for the awkwardness of what just transpired there. But I've got two things that give me a constant. All right, and what's between those two constants? Or what's between 0 and minus b over a? Minus b over 2a, which centers the quadratic. So that's one insight. The other insight was that if you look at 5x squared minus 20x plus 7, and you let x equal 0, then you get 0, 0, 7. But if you put in 0.001, you get, it's going to run off the board here, you're going to get 0.000005 minus 0.00020, 3 decimal places. So excuse me. So I just want 0.02. I forgot I was doing 3 decimal places. So over here, squaring gets me to the 6. This one gets me to 3. And then it's still 7. All right, well, there's no changes with the constant. There's minimal change there. That's your most significant change of these 3 terms. And if I divide that by 0.001, I can see I'm going down at 20 to 1. And I don't think that's a coincidence. And now if you look at it graphically, you can start to move towards calculus when you look at 5x squared, which is a narrower parabola than x squared. In other words, every y value is just 5 times bigger than the 0, 1, 4, 9 outputs, right? It would become 0, 5, 20, 45. So things are happening more quickly. And it still has a vertex of 0, 0. I'm looking at 5x squared, right? Minus 20x actually is a linear function that intersects at 0, 0. I'm sorry, I'm going to do minus 20x plus 7 instead. So minus 20x plus 7 is just a linear function that goes through at a height of 7 and goes down quickly, like that. Now, if you look at rates of change, this is flat here. And there are some videos made. I think the geometry to algebra to calculus in 20 minutes kind of hits that theme. All right. So I have a flat rate of change from the quadratic term, but this linear function is therefore going to be the rate of change at that instant. And we're going to add up the two y values, 0 and 7. So I'm really getting the y-axis, I'm really getting a tangent to 0, 7. I'm kind of zooming in now, and it's going down in 20 to 1. But I know it goes back up, right? So there's levels of that we can delve into. Deeper understanding, conceptual awareness is what we can have now as we continue to talk about these problems until May 15th, right? So we're up and running, but we don't want to stop there. We don't want to just be able to graph. We want to try to get into what's going on from the standpoint of rates of change. How are the rates of change of each term allowing us to visualize this a little more deeply, right? So that's that problem. And of course, with every consideration comes a deeper consideration, and I'm asking you to be able to spot your roots at 2. That's an x value, right? We're measuring from this x value. We want roots. So what's going to take me to heights of 0 here and here? Well, it turns out it's the square root of, where am I? Minus 13 to 0, 13 units of change. And my multiplier was what, 5? Okay, well, that's not hard. I'm a little too close to the board sometimes to see the numbers I'm working with, which causes me a lot of careless errors, but don't know how else to kind of express this information to you. So I hope I didn't make any careless errors. I got my good buddy Yasser over in Lahore. You can correct me, but what I'm talking about conceptually has validity, and I'm hoping that as you keep doing these problems, okay, I know how to do it. I know how to graph. Well, great, but there's a lot more that you can learn if you dive in more deeply. And I don't want to stop that process, but, retiring in a couple of months, so we'll see what I'm going to end up doing. But I'm trying to share the fact that, I've done a couple of 100,000 of them. I ought to be able to see a few more things. Certainly not native ability. I can tell you that. So can a lot of other people in my life. All right. Y plus 6, 5 times x minus 4. All right, what do I see? I see 4, negative 6. I see 4, negative 6. So I just put a dot there, and I see I'm going down at 5 to 1. Okay, so there's 4, negative 6. And if I'm going down at 5 to negative 5 to 1, well, then what I basically did is I just changed my change in x, 5 to 1, down 5, minus 11. That should be there. Now, that was what I wanted to highlight. Normally, I write things like 2 over 3, and I ask for 3 coordinates. 3 coordinates. Well, you'd start with 4, negative 6. This is what we've been doing on the previous lesson sets. Add 3, go up by 2. That's what we've been practicing, right? So I decided to hide that triplet, right? And hope that you did what? You, in your mind's eye, put a 1 there. Yeah, that's all. It was just a little bit of can we push a little forward? I've got your muscle memory here with, different change in y over change in x. And now I had hid the change in x. And maybe that made you think a little bit. And I hope I didn't make any mistakes there. All right. Now, to understand, well, I'm just going to do it. So negative 3, comma, negative 8, endpoint, square root looks like that. I'm going to throw a 22 in there. That's a nice user-friendly number. You can do the math now yourself. Minus 10, I got minus 18. All right, so there's the graph. That's what I'm hoping to see on a test. But I am hoping that people look at it a little more carefully. What's my change in y? Looks like I've gone down 10. And here's the kicker. This is where change occurs. Right? That's where the change is occurring. As I put values in, this number is changing. And people do so many linear functions at Algebra 1 that when I say drop a 22 in there, people say it's changed by 25. Well, you got to get that out of your head. It's changed by the square root of 25. And what is this number? Well, that number is -2. And where do you see that number? Right there. So you want to make the connection that that is rise over the square root of run as measured from this endpoint. Now, I've talked about all of these things before at different times, but now I'm hoping it's sinking in because you've got the mechanics, you're starting to work with it quickly, and I want to encourage you to look more deeply at what's going on. I've learned some things this year about quadratics that I didn't know. Learned some things about logarithms I didn't know, and I've been looking at these things for years. I don't think you can stop that process. That's my message today. All right, so I'm going to graph this real quick and then talk again a little bit about some insights that I've seen over the years. So I'm going to do this. I'm going to do 4 plus 5. I'm going to get, let's see, 12 plus 5. I'm going to get 17. I'm going to get 9. If I pick the right numbers, and I think I want minus 1.1 to get me 17. And I think I want 0 to get me 9. And I believe I'm looking at y equals 5. So to do that in a more visual manner here, -1.1 should get me 12 and 5, 17. I'm doing it again in my head. I already forgot what I said before. And a 0 should get me 9. Okay, that's that graph. Now, where does the ability to spot exponential decay come from? We've practiced that. That means I'm doing 1 over e to the x. That's reciprocation. And that's approximately 1 over 2.71 to the x. Well, if I start with a number 4, and let's just round that to 1/3, and I do this, well, where's that number going? Where's that number going? Where is 4 to the 1/3 to the x as I move towards positive infinity? Doing it not once, but twice, but 3 times, forever. If I keep doing that, I think I'm going to 0. I think I'm going to 0. But if I added 5, well, this is going to 0. That's a constant. This thing is heading to 5. I hope that gives you a little better feeling of the asymptotic behavior. And you can think of this as a trend. Where are my table values trending towards? Where are they trending towards? They're trending towards 5 because this is the decay part. That's the decay part. Okay, so how did I arrive at those approximations? Well, I looked in a calculator and I said, well, when does e to the x equal 3? And the calculator had a button I pushed, and it's the ln of 3, and I think it was 1.09, and I forget the rest of it now. But I called it 1.1 just so I could work with it. And so I got real familiar with the tripling process. That's the tripling process, which is pretty darn close to e to the, actually 1.09 is a little better than 1.1, but I don't see a problem with that. All right, those are very similar functions. So I know I'm pretty close to the same kind of shape. If I put a minus sign there, then it's reciprocation, right? It's 1 over 3 to the x. So instead of a differential that is 3 times bigger, we get the 3 times bigger and then the smaller one looking like that. All things that I want you to discover as you continue to work at these things. Keep your eyes open. Don't just say, oh, I can do that. Okay, it takes me 30, 40 seconds. Great. If you keep looking at it, it might take you 3 to 5 seconds to graph it. And when you're working with a lot of problems, that's a nice thing to know. So I know when I see a minus x, I'll do another one for you. All right, I'll put in the differentials. Let's just throw another one, random one up here. Let's look at 12 e to the x minus 5 plus 7. Let's graph that. All right, so wait a minute, I want 5 minus x, I guess. I wanted to give you a decay problem, right? So I see minus x, then I immediately do this in my mind, and I want a 3 to 1 ratio. What's going to be 3? The one that I have 12 times something, right? All right, so let's just look at it. I want 5 minus x to equal 0, and I want 5 minus x to equal 1.1, because I want a triple. So that's going to be 5 minus 1.1 is going to equal x for this one. And so that's what? 3.9? All right, so it looks like 3.9. When I plug 3.9 in here, I get 1.1. So that's 12 times 3, there's 36, which means this one's going to be 1/3 of it, roughly. Well, I got to be careful here. I got to be careful. So 5 minus x, I want that to equal 0. I want 5 minus x to equal 0. So I simply move to the other side. I can see 5, right? And if I get that, I get 1. E to the 0 is 1. That's 12. There's my 3-to-1 ratio, but it's decreasing. So the next one's going to be 4. The next one's going to be 4/3. And what am I heading towards? I'm heading towards y equals 7. All right. I know I'm talking about it and I'm really not putting the numbers in there, but 3.9, 1.1, 36, 5, that's 0, that's 12. So if I put 5 in, I get 12. And I'll clean this up quite a bit. Won't show the differentials, but I hope you can see 7 to 36. I just made a mistake, darn it. 7, I forgot to add the 7. 43, excuse me. All right, so 43, take away 7. There's my 36, right? There's my jump. My first jump was here, and I know I'm going to end up tripling it each and every time. I'm going to standardize that so that I can quickly get something on an answer key. When I'm doing 70 problems and I'm doing 3 tests in a particular day, that's 210 problems I got to do. You know, and I can't waste time doing that. And I can't find this kind of process in a textbook. The closest thing is, well, I don't want to be advertising, but you know, there's some textbooks that do this, but I'm not sure they tie it together templatively. And that's what I'm trying to do here. All right, so from the last problem, what are you seeing? I'm seeing, boom, boom, boom. I'm seeing a 3-to-1 ratio. And I know my first jump is 10. That's going to be 30. That's going to be 5. So what are these values? 10 plus 5, 15. 5 plus 35. Plus 30, 35. I've got those provided I can find the right x's. Well, what x's do I want? I want to make a 0 and a 1. All right, well, that's 0. And that's 1. And so therefore, without the differentials there, I've got something that's tripling, right? There's your differentials. All right, let's see what happens when I put in a 0. 3 to the 0 is 1. That's my first jump. 10. 3 to the 1 is 3. 3 times 10 is 30. And remember what 3 to the x is. 3 to the x is taking the number 10 and it's tripling it. It's tripling it. It's tripling it. It's tripling it. So I hope you understand 10, 30, 90, 270, so on and so forth. When? Every time I change by 1. Every time I change by 1. All right, so let's try another one. And let's do our differentials, ratios of change. Let's look at a doubling function. Let's look at how about we do 4? Let's do 6. Let's do 6. Let's double it. Let's start x minus the year 1900. Let's change every 50 years, and let's put that on top of 7. All right, so what do I see? I see y equals 7. I see my first jump is 6. My next jump is 12. My next jump is 24, and I'm off through here somewhere, right? So boom. So 6 and 7, 13. 7 and 12, 19. Let's get rid of all of the stuff that we don't need that's in our mind's eye. What are the x's? Well, I'm hoping you'll look at this and see that as 1900, 1950, 2000, 2000. All of these are user-friendly numbers. What do I get when I put 1900? It's 6 plus 7, 13. Then I've got 12 plus 7, 19. Then I got 24 plus 7, 31. Lots of data coming at you quickly if you spend the time to go search for it. And I'm saying that's time well spent, especially if you're a teacher and you got to do hundreds and thousands of these things. Okay, so 1900 should get me 13. Let's see if it does. 1900 minus 9, 0, 2 to the 0 is 1, times 6 is 6, plus 7, 13. And let's put 1950 in here. 1950. Oh, that gets me 1. 2 to the 1 is 2, times 6 is 12, plus 7, 19. If I put in 1950, right, the next one's going to go up by 6 times 2 times 2, because that's what 2 to the x means. Keep doubling as we move from left to right. Well, what do we do if we're moving from right to left? We're not doubling every 50 years. We're cutting in half every 50 years. And if you look left and you cut in half, well, that's an altitude of 3 now on top of 7. That should get me 10 units if I pick what year? Not 1900, 1850. 1850. So you start to see a lot of data. Now, what happens when you put 1850 in? You get minus 50. And what's minus 50 divided by 50? It's minus 1. And what is 2 to the minus 1? Yes, I'm cutting in half as I go in the other direction. So I'm hoping we make the connection, just like we did with a line. What do you do when you have a linear function that passes through 5 and 9? You write x minus 5 over 4. That's what you do. Well, that 4 could have come here. All right? And I'm hoping you start to spot that. Well, didn't we have that with this problem? X minus 1900 over 50. Well, I'm hoping you're jumping over here and saying, oh, wait a minute, my brain's doing this. Those are the connections I'm hoping you'll make. Not just do this, get that, but do this and understand that. Well, there's the 1/2. So, boy, I've got a lot of exponential functions here. So I'm going to have one of those, where my first jump is 12 and my second jump is 6, and I'm on top of 6. So let's change that right now to 10. All right, I'm on top of 10. Well, I know 10 plus 12 is 22. I know 10 plus 6 is 16. I know my next one is going to be 3 because I'm cutting things in half, and that's going to be 13. So I can put some table values in here right now. Looking at this, I can see 5, I can see 12, I can see 17. Should match up with 22. 1/2 to the 0, 1. 12 plus 10, 22. Should match up with 12 when I pick the number 12. 12 minus, that's 1. 1/2 of 12 is 6, plus 10, 16. Oh, good. So far, so good. Let's go one more notch. Let's put 17 here. 17 minus 5. Oops, I made a mistake here. Change by 7. Oh, change by 7. I caught it. Okay, 19. So I want to put 19 in there. 19 minus 5, 14. How did I know I had a mistake? Because 14 is a multiple of 7. And when I got 2 seconds ago, isn't a multiple of 7. Because I'm trying to find user-friendly numbers. So doubling, squaring 1/2 is 1/4 of 12 is 3. And 3 plus 10 is 13. And so we can see those numbers quickly and easily with enough practice. The sine function. Well, I know the sine function. One period starts at 0 and ends at 2 pi. All right, and I know that it goes to a height of 1. The midline is 0, and it goes down to -1 because the sine function measures height on the unit circle. And as I draw triangles, I start to get height. Maybe that's a height of 1/2. Maybe that's a height of √2 over 2, about 0.71. Straight up and down, 1. Straight down, -1. So I know as I move around the circle, let's make a smaller circle here. As I measure heights along the circle, heights go up, they go to the midline, they go down, they come back. And then they repeat. This is one period. Kind of a mountain shape, valley shape. Because you got to have shape in your mind before you can keep looking at values. And so how do these values change now? Well, I can see 4. If I divide 2 pi by 4, then I know the period of this function is 8 pi. I know that. And we'll develop that in the second half of the term. All right, so I now know that I go from 0 to 8 pi. Boompity boompity. And I know that my midline is not 0 anymore. The sine of x has a multiplier, it's 1. It has a constant, it's 0. And that's really a sine of x plus b format. All right, it's kind of that format. So I know my midline now is 10. And I know that my amplitudes are 2 times this. So I'm going up and down 2 units. 2 units from 10 puts me at 12. 8 pi, 4 pi, 2 pi, right? There's a lot of symmetry here. So there's some stuff that you can get up on the board pretty darn quickly. All right, now how did I know my period was 8 pi? Because this regulates how fast I go around the circle. And that is really 1/4 times x. So let's say x, which represents angles. And I go around the circle at a certain speed. And I start at 0 and I end up at 2 pi. That's my traditional once around the circle. Well, what if I go 1/4 as fast? So that's the speed to go around. I'm going to go 1/4 as fast. Well, it's going to take me 4 times as long to get around the circle. Okay, so by solving x over 4 equals 0, that's the start of the revolution, Goche. I don't know if I should do that or not, because I don't really know much about him. I know he had good intentions, but whether or not he was on the right path or not, let's leave that for the history classes. All right, and x over 4 equals 2 pi. Well, there you go. Once around, sine of x, once around, and now takes 8 pi. Or 8 times 3.14, about 25 what? Units. So if I have a circle with that, not too bad, that's 1 radius length, I got to do 25 of those. 1, 2, 3, 3.14. Why don't we call that pi? Forget, we're working with numbers. 4, 5, 6, 6.28. I got to do that how many times? 4 times. And so that's roughly the period here is about 25 units, about roughly. All right, let's keep moving. More in-depth analysis here than, previously, because I hope we're building our understanding. All right, so x equals 4. I know this is the inverse of growth. So what am I going to pick? I'm going to pick the number 3 because I'm using the ln of 3 to help me. It's about 1.1. All right, so I'm going to pick 7. That's going to get me 1.1, 7.7 plus 5, 12.7. Okay, and I also know that the ln of 0 is undefined. That's what allowed me to say, oh, I need the number 4 because I need positive numbers here. This parentheses has to be bigger than 0. Oh, we're not going backwards from growth, right? Time, something's growing. This is the inverse. Well, that's something better exists, or I'm not going to tell you how it's growing or decaying. So what we have in here is the quantities from growth and decay, and we're going backwards. And so I now know that 1, right? The ln of 1 is 0 because I keep hearing it every single day. I keep working with it every single day. I know that e to the 0 is 1. And so this is base e, and that's the way we say it backwards. Inverse operation. So I'm going to make this thing 1. And that gives me the number 5. And if I make that 1, then the ln of 1 is 0, then I don't have to do that multiplication, and I can see that number immediately. And you keep practicing that becomes a 3-second graph. Understanding the asymptotic behavior here, well, that's understanding negative 1.1, right, is going to be a third of this. And so we have these differentials. My first differential is 1. How far is it from 4? I erased my 4. How far is it from 4 to 7? 3. Well, that's kind of the inverse of what we were doing with e to the x. So we'll develop that further because I might be losing you now. But we'll keep talking about that till maybe you see it. Now, why am I doing this here? Because there's a lot of gaps from Algebra 1 that we're trying to close. Folks didn't get this practice. Okay, so what is x to the 4th? You need to know the shape. Well, I put a 0 in first. I don't think I can get smaller than that because it's an even power. So let's put 1 in. 1 to the 4th is I almost said 4, is 1. How about we put a 2 in? 2 to the 4th is 16.
3 to the 4th is 81. We've worked with all those numbers. And -1 gets me the same answer, and -2 gets me the same answer, and -3 gets me the same answer as those. But what happens if I put a half in there? Well, a half gets me 1/16. Geez, that's a lot smaller than what I started with. So I'm seeing a graph that decreases, increases, right? And is a little flatter than x squared, let's do that, a little flatter than x squared is. And so there's my 0, 0. There's my 1/16, so forth. And that's going up very quickly here. So the scale I gave you, 1 gets you 1, sorry. 2 gets you 16. All right, so there, that's a little better. 1 gets you 1. All right, okay. And symmetry on the other side. So what happens when I put it x plus 2 here? Well, I got to mimic the 0. So it looks like that's now -2. And that's now -1. And that's now 0. And that's now 1. And that's now, I'm losing track of my -3. And that's -4. And that's -5. I hope I did that right. I'm pretty close to the board here. All right, but I had to do some point-by-point analysis, and that's where it starts. In your first year of algebra, you gotta work with numbers, and you still do, except some of the numbers get a little more interesting, like the ln of 3. Okay, all right, so what's the sine of 3? That's the same exact question I asked about 2 tests ago. Now, why am I asking it again? Because I know nobody understood it the first time I asked it, and I understand it takes time to learn. So let's look at it again. So if I have a circle like that, and I erase a big part of it, I'm left with something called an arc. I didn't even spell it right, too close to the board. An arc, all right? An arc is a portion of a curve, and that's curvature, okay? So in fact, the inverse of sine is actually arc sine. I might as well talk about it right now, where that x now stands for the ratio, and we want to get an angle. And so what's the arc sine look like? This part of the circle from 90 degrees to -90. Those are my answers. If I put a 1 in, the arc sine of 1 is 90 degrees because the sine of 90 degrees equals 1. We're going to be doing that in the second half, so it doesn't bother me to mention it for 2 minutes, because you got to start conversations. And because I'm talking about an arc, that's what comes to mind. Don't expect you to understand how to do that yet. We haven't even done the unit circle, but we are going to really soon. So this measures distance around the circumference of the circle. So I got to start somewhere and make a circle. There's 3. The more famous number you know is 3.14. So now I got to blow this up. There we are. There's the arc. Let's make it even. Zoom in a little bit more. There's the curvature. There's 3.14. Here's 3. That's almost straight up and down. So what do? We draw circles by going over up to the circumference intersection, and then we start talking about heights and widths, sine function, cosine function, because we don't really need to divide by 1. Right? And if I doubled this, the angle doesn't change. The ratios are congruent, right, from your geometry classes. So it doesn't matter the size of the triangle. In a right triangle, the ratios of those triangles stay the same. All right. So you have h over this distance. Well, I can tell you what the arc distance is. It's approximately 0.14. Well, what's that height then? I think it's approximately 0.14. They're almost identical. Now, the altitude is getting smaller. As I move this dot down that arc, that height's getting smaller, but the distance is getting bigger, which means the rate of change, the x, is the measurement of the circumference. The circumference change. So let's put circumference change, right? From 3 to 3.14 is about 0.14, and it is getting bigger. This started at 0.14, but it's getting smaller, but it's still almost 1 to 1. This one is going down, this one's going up, but it's almost 1-to-1. And what's the sine function look like at pi? Right there. Well, the table value is almost going down at 1-to-1 right there. All right, so I don't care what question I ask you. There are deeper and deeper and deeper analyses that go with that. The next step is to look at the chain rule based on this location. So if you're studying calculus, somewhere I did one where I think I looked at the sine of x squared, right? And without a calculator, played with the chain rule because we're so close to 1-to-1. And I think the answer came out to about 1/10,000th of a decimal place off, or 1,000th, even if it's only 100th. You're getting a feel for the chain rule because you got an understanding of some of the numbers over here. You're not going to get that understanding unless you try to listen, think about, listen again, think about. I mean, remember, I'm doing this for the last 45 years. You're trying to shorten that process so you can go up the ladder in the discipline. So good luck. All right. Oh, we had a nice warm day here today, but it's going to go down to 0 to below 0, I think, tomorrow night or the next night. So we're not done with winter here yet. So stay safe and warm. All right. Ciao.